Mm. Periodic table. A student gave me this. I love it. I have a couple. I love it. Love all of them. Hi, good morning. This is my long morning. Still going. I think this is going to be the last one to do because the person I live with is like, well, maybe we'll do something when you stop working. So I think this is my last video from the morning. Maybe I can sneak one in later today. Last one on stoichiometry. This is going to have a little trick in it. It's going to be short like the last one. Call it stoichiometry with a redox trick, just because you're going to see it on worksheets. And I want to make sure you know what to do and you don't feel like I left you out there in the cold. Okay, so I'm going to share my screen and head over here to this wonderful iPad that Miss Ellie shared with me. Thank you, Ellie. Love it. Love it. Okay. So we have just another stoichiometry problem, but it reads tricky. So I wanted to just go over it with you. We've got 35 milliliters of a solution of a 0.230 molar lithium chlorate. Okay. Well, when I look down here, I don't see anything that is lithium. I'm sorry that my numbers aren't small and subscripty. I need to fix that. That's because lithium is a spectator ion, right? Group 1A ions and all of those other ions that are always soluble are always spectator ions. Okay, therefore you're not going to see this in the equation provided, and that is likely to happen to you in your work on your AP exam, on your worksheets in here. Students go, well, I don't see it. That's because it's the net ionic equation. All equations from now on are pretty much, you know, if they're AP, going to be net ionic equations. So you need to realize that this right here is referring to this right here. Okay. And let's continue reading. Was added to acidified chloride ions. Acidified is this. Let me give you color. Acidified is this. Okay. It's just wording, trying to confuse you, trying to trip you up. Chloride, oops, don't want that. Let's just skip that. Chloride ions would be the chloride ions right there. Okay. Okay. The chlorine produced reacted with 23.5 milliliters of potassium sulfate, that's K2SO4. Potassium, once again, is a spectator ion. So all we see here is the SO4 2 negative right there. Okay. Calculate the concentration of potassium sulfate. That is moles potassium sulfate per liter solution. All right, that right there is our answer. Right, you've got to know what you need in order to get the answer. This is what we need. So let's see if we know anything else. Given the redox equation below, we have not studied redox. We will soon, and then we'll study it really good later. Redox is the best. So what do I know about my potassium sulfate? I know that I have 23.5 milliliters of it, right? So let's go ahead and get that into our liters. And we know that that's going to be this many liters of K2SO4. All right, labels are good. All right, let's look at what I have the ability to clean this up. So I'm going to do that. Okay. Okay. I've already used that number. I've already used that. What's missing? Let's write our data down here. I've got 35.0 milliliters of a 0.230 molar. And I did in my head notice that this is a 1-to-1 ratio, okay? So therefore, that's how many moles of chlorate I have. Well, anyway, I just for some reason said that. I don't know. Now, was added to chloride ions. The chlorine produced, so look here, guys. This is the chlorine produced right here. All right. It came here, right? And it then reacted with this, right? So my stoichiometry is going to take me from here to here. And then I'm going to go from here to here. All right, I'm allowed to do that. Just follow the roadmap. Okay, so I'm going to start with what I know. And right here is what I know. Okay, so I've got 35.0 milliliters. Every 1,000 milliliters is 1 liter. Every 1 liter, according to the molarity, is 0.230 moles. Now let's get a label in here so that we don't lose ourselves. Let's do our stoichiometry. Every 1 mole, according to the equation up top, is equal to 3 moles of chloride ions. I'm now going to convert my moles of chloride ions to moles of sulfate ions. Okay, and if I look at my equation, the ratio for that is 1 to 2. So that's 1 to 2. I could go ahead and finish this and see that there's 1 mole of sulfate ions in every 1 mole of potassium sulfate. Boom. And then I will have my answer. So we've got 0.035 times 0.23 times 6 equals, and I have 2.42 times 10 to the negative second moles of K2SO4. You know, you might want to do it again, but I look up and it looks like I did it. Oh, no. I didn't get a 6 in there. I only got a 3. So I need to times that by 2. Let me make sure. Let me make sure. 0.035 times 0.23 times 3 times 2 equals, yeah, that's wrong. So I looked at my calculator. I saw that I made a mistake. 4.83. So I, do that times 10 to the negative second, or just do it twice if you have time. But, always kind of look, because it's easy to make a mistake. All right. And remember, this is what we needed, right? What we needed was the moles per the liter. We've got our liters right here. We've got our moles right here. So to answer the question, the concentration of potassium sulfate is equal to 4.83 times 10 to the negative second moles over the 0.235 liters, and divided by 0.235 is 2.06. And that's it. All right. I'm probably going to go ahead and make another video. I love this stuff. Love it. Okay. That's it for stoichiometry. Bye. Have a good day. Stop. See ya.